that, you know, the talk is at deep in the night. Thought again, you know, because I haven't slept, so I could fall anytime in my talk. So, you know, so, but it's very exciting to be here. Thank you everyone for coming for this talk. I see some of you, for example, from a couple of places sitting on a big room with mask and looking forward. It seems like a screen probably in front of you. Quite exciting. And probably Ethiopian coffee somewhere around. I can't see it. And Kolo, I had Kolo here. That keeps me going. So it's wonderful to be here. So what I'm going to do is I'm going to try to tell you about what we do in my lab. And I gave the talk this title, Probing Quantum Materials of the Nanoscale, quite a mouthful, so I'm going to define some of this as we go along. I am at the University of Georgia. It is about an hour away from Atlanta, a beautiful city, amazing city. And you know, one of my subtle goals of giving this talk is actually to see if I can recruit some of you smart students sitting there looking at this. I am really actively looking for graduate students in my group. So if you are interested, please email me. This is my email right here, johannes.abate@uga.edu. And we have also a website. This is my group's website. If you just open the browser here, this is my website. So you can go there and see what kinds of research we do. And we have a number of students here in the group. These are my graduate students. Currently, I have only one postdoc, and several others have gone out of my group into, you know, academia. Victoria is now a professor, and others have gone into all kinds of other places. So, so I think those of you who are interested can connect with me, and I promise you that I will support you in anything. For example, for TOEFL, and you know, any of those things I will take care of. So all you have to do is just connect with me, send me your CV, and we can have a Zoom meeting and go from there. Okay. So let's dive in at almost 2:30 a.m. or 3 a.m. The nanoscale. This is one of those exceptional days. Okay, so as you all know, size is quite important in physics, right? In science. The reason for that is, you know, for large things on this direction, like if you take planets or, you know, very large, big things. And then you come down to balls and even the size of bacteria and so forth. Newton's laws work very well, right? Particularly F equals ma governs all of this, and you can describe the dynamics of things by using that very simple equation. And also Newton's gravitational law also works pretty well. But when you go down to very, very small size scale, like atoms and subatomic particles, Newton's laws fall apart, right? You cannot follow the trajectory of a particle. The trajectory is not defined. And all other new things start to appear. And so Dr. Seifo had done a great job of introducing quantum a little bit. And that is the kind of physics we use, quantum mechanics, right? But then there is this fuzzy size range, which is roughly between 1 to 100 nanometer length scale. It's called the nanoscale. And it is quite interesting because it is sort of, it combines both of these physics, right? The physics of the big scale and physics of the small scale in a nice way. And as a result, a lot of interesting properties appear in this size range. And that is the size that I do my work. It's quantum phenomena. Several materials, I'm going to show you a few of them that exhibit a very prominent quantum property. And those materials are what we call them as quantum materials. It's a kind of buzzword these days. You have to say quantum materials, but it just refers to materials that have a prominent quantum effect to describe them. And one person who envisioned this kind of physics, the physics of the small scale, not necessarily on the atomic, subatomic scale, but in the nanometer length scale was Richard Feynman. So those of you, some of you probably know him. He is one of the he was one of the leading physicists, and he won the Nobel Prize in 1965 for quantum electrodynamics. And he actually gave a talk on this in 1959. Think about this, in 1959, before even the field started, right? He was so visionary. He gave a beautiful talk in 1959 at an American Physical Society meeting. A meeting like this one, of course, in person in those days, and the transcript of that speech is now a very popular write-up. It's called "There is Plenty of Room at the Bottom," and those of you students absolutely recommend this write-up for you to read. If you just Google, if you have internet access, "Plenty of Room at the Bottom," there's just a PDF version of the entire talk, and I absolutely recommend for you to check that out. It's a very nice introduction to this nanoscale physics, nanoscale phenomena, and the potential there. And also, if you just shoot me an email, I can send you the PDF file. So in that talk, he mentions many interesting problems and also kind of potential applications of nanoscale. And one important thing that I kind of highlight here is as we go down in size, it's not like you can just scale physics down. It doesn't work that way. There are some new things that you have to deal with. For example, in the macroscopic scale, these van der Waals forces, these are electrodynamic forces between materials, are negligible, right? You can ignore those kinds of interactions. But as you go down in size, these kinds of forces become very important. And in the macro scale, in the scale of us, the scale of these kinds of structures or size, gravity is very important, as you know, right? But when you go to this small scale, gravity is less important, almost it's irrelevant. And so things become very, very different for that reason. And as a result, you have some new phenomena that materials exhibit. In fact, any material you pick, anything you pick, and you chop it down to a few hundreds of atoms, or even to a few thousands of atoms, then its macro scale properties that you read from a book or that will become completely different. So this is, the material starts to exhibit a very new, and sometimes spectacular properties. And my fun job is to study this, basically. So so I have a really great job, just explore these new phenomena that appear in this length scale, and particularly those that are quantum mechanical. So now, when you want to study these kinds of things, I think somebody wrote something on my screen. So I'm going to try to get rid of it by, let's see if I can annotate and get rid of this write-up. Yeah, cool. So, yeah, so when you want to study something like this with light, we use lasers to study these kinds of phenomena, you will have a problem, right? There are two important limitations, experimental limitations you have to overcome. The first one is well-known, the diffraction limit. Okay, this is actually the original paper from Abe in 1873, who came up with the term and who understood this limitation. It very simply says the following. If you have 2 points or 2 things and you want to see them separately, you want to resolve them, the minimum separation between those 2 things must be the wavelengths of light that you use over 2. If their separation is smaller than that, you cannot resolve them. They just appear like a blob, one thing. So, this is a limitation one has to overcome, and it is not. It's a limitation because of the lens you use. So, in the focal plane of the lens, your resolving power depends on the wavelengths of light, and that is roughly the wavelength lambda over 2, the wavelengths of the light you use over 2. Right now, for example, we use the visible light, say around 600 nanometer. So anything we can resolve at best is about 300 nanometer. So, but these nano things I'm talking about are in the order of tens of nanometers, very, very much smaller than the diffraction limit. So so you cannot study these individual particles by simply focusing light with a lens. So this is one limitation you have to overcome. The second one is less known. You may have heard of this from optics class, but this one is probably less known to most of you, and that is the mismatch between the momentum of light and some quasi-particles, some propagating particles that I will tell you about called polaritons. For example, there is a momentum mismatch. The momentum of light is very, very small. As you know, light is massless. It has a momentum, but its momentum is linear with respect to energy. Right? So if you draw the energy of light as a function of its momentum, you find this line. It's just a straight line. It's called the light line. Right? So there is a linear relationship between energy of light and momentum of light, always, at any time. But these quasi-particles, for example, these polaritons, are massive, more massive than light, and their momentum is always smaller than that of the momentum of light. So light cannot really couple easily, even if they have the same energy, but one is moving faster than the other. So, the light cannot excite these kinds of particles. So these are the two sort of important limitations one has to overcome to study nanostructures or nanoscale phenomena using lasers, using light. So I'm going to show you a technique that overcomes both of these limitations in one. Okay, a very powerful technique and a very simple technique, but extremely powerful and allows you to investigate nanoscale phenomena with a much higher spatial resolution. And this technique is called scattering type scanning near field optical microscope, or s-SNOM. This is a mouthful. All what it is just a very sharp tip, like a needle, very, very sharp tip. And you, instead of using an objective, some kind of lens to focus light, you focus the light on the tip. So then that tip confines the light further for you. to a limit only determined by the apex radius of the tip. So this is a nice cartoon. This is kind of a sharp tip, and I shine lights, and you can see a very intense field around this tip. So now, instead of your objective, your lens, your light source is the tip itself. Imagine this it's like a flashlight that you want to see these nanoscale things with using it. So now your resolution, the beauty of this technique is your resolution is now limited by the size of the tip, which you can buy these days commercially by, you can get 10 nanometer or 20 nanometer radius tip very easily. So you beat the diffraction limit just like that. The other advantage is it breaks the momentum mismatch between light and other quasi-particles. So I will tell you more about that as we go along. And your resolution is no longer limited by lambda. It's not lambda over 2 or lambda over 10 or something like that. And instead, it is independent of lambda. That means if you use a visible light or a very long wavelength light, like a terahertz, very large, very small energy light, it doesn't matter. It's irrelevant for as far as resolution is concerned. Just is determined by the size of the tip. So this becomes extremely powerful in that way. So we use this kind of technique, but I want to now tell you a little bit more about this kind of technique, how a technique like this can give you, information about a nanoscale phenomena or a quantum phenomena of things. Okay, so I'm going to just kind of show you a simple cartoon. So imagine this is your sample. This is the sample or the material you want to study. And it has some fancy quantum phenomena in it, but you really are oblivious to what's going on there because you can't see it, right? It's just the things that happen there are at a very small scale. So what do? You bring your tip. Imagine this is your tip, and then you shine light on the tip. So it's a very simple approximation. Think of the entire tip as a sphere, okay? Just forget about the structure of the tip and just think of it as a tiny sphere of 10 nanometer in diameter. So if you just ignore all the structure of the tip and imagine a sphere, when you shine light on it, what happens? Light is an electromagnetic wave, and you can forget about the magnetic field because the magnetic field is much weaker than the electric field in light, right? We have E and B, and as you know, E cross B give you K. So light propagates along the K axis, but it has E and B, and E and B are related by C. So E is much larger than B at any time. So forget about the magnetic field. So when you think about light, think of the electric field and think of it as a sinusoidal wave, right? These are, we don't look at a single photon, right? We look at many photons together. So, so you can think of this as a wave exciting or hitting this sphere. So what happens? The wave oscillates. That means the electric field goes up and down, right? When it does that, it excites this sphere, right? It excites. So that means when the electric field is up, all the positive charges go down. That's right? No, go up, and all the negative charges go down, and vice versa. So you can imagine, as the laser oscillates, the charges on this polarizable sphere also oscillate. So you can think of it as a dipole, really. So it's a dipole. The charges oscillate up and down, positive, negative, with the frequency of the laser. And what happens when something oscillates? It emits, right? The dipole is an emitter. So there is an emission going. But the other thing that happens is, as you bring this thing close to the sample, your material, it polarizes the material, yes? Because when you excite it and say that the electric field is up at one point, then all the positive charges are up and the negative charges are down. So the negative charges are around here and it's close to a surface. So what it does is it brings up all the positive charge close to the surface up and the negative charge down. That means you can think of this as an image dipole generated close to the sample. And that image dipole, whenever you have a dipole, you have an emission. That's what dipoles do. They oscillate and emit light. And that is the light that kind of scatters away. And that's what we measure. And this scattered light contains information about the sample, because it's very easy to show that this dipole has an image dipole in the sample, which is equal to this beta times P, where beta contains the dielectric function of the sample. So it's called the surface responsivity function. It's E minus 1 over E plus 1. The epsilon minus 1 over epsilon plus 1. So that epsilon is what you need. As it scatters away, it takes information, which is the optical constant of the sample. In this way, you map at small scale the optical properties of the sample as you scan this tip on your sample. So this gives you a very cartoonish view of how this technique works. And when at the end, what you would get is 3 images. Because it is based on a tip, you get topography. It maps the topography of the sample, and it gives you also amplitude and phase. So you can think of these 2 images as amplitude being the real part of the dielectric function and the phase being the imaginary part. Or you can think of it as the real part, or scattering how the sample scatters light, and the imaginary part as how the sample absorbs, the absorption property of the sample. So in one go, you kind of map both topography, scattering, and absorption of the sample. So in this way, we can learn really everything we need to know how a sample responds to light by raster scanning a tip like this. Experimentally, there are some challenges. It's not as, in principle, easy. In practice, you have to overcome experimental challenges to make something like this work. And let me show you some of those challenges. So imagine this is your tip. You bought this very sharp tip. It's apex radius, say 10 nanometer or so. And now you brought an objective and then a detector and your sample. And you arrange it in this way. Then you shine light. When you do that, yes, the tip confines and focuses a laser for you and beats the diffraction, but you won't learn much about the sample in this way. The reason is the background signal is much larger than your this confined nanoscale light that interacts with the sample. Just so overwhelmed by a huge background. Just to give you a feeling, if you use 1 milliwatt laser, your signal here that scatters, that gives you this nanoscale information, is in the order of picowatts. Orders and orders of magnitude smaller than the excitation laser power. So your detector is overwhelmed by a simple scattered far-field lights, and you won't be able to learn anything. So you need a way of filtering this out, and we do that by what's called harmonic demodulation. We oscillate the tip at some resonance frequency, and then we only look at the signal at the tip frequency. And we can get rid of all the scattered light by the tip oscillation by going into higher harmonics of the tip oscillation, by using what's called the Lockean detection technique. So I think that's a very powerful technique that allows you to filter out this nanoscale interaction. And when you do that, your signal becomes weak. Then you use interferometer to enhance it. And that way you get also a phase information. Whenever you have interferometer, you have a phase information. I see a hand, Ellen, is that deliberate? Or?
Yes, I have a question actually.
Sure, go ahead.
Is there, so am I right in assuming that the diode that's on the cantilever or the AFM itself is also going to that same detector, or is there two detectors, one for the deflection and one for the light that's on the sample?
Excellent question, Aaron. I see that you're familiar with AFM. So, okay, so just to describe the question for the rest of you, what Aidan is asking is the tip as it oscillates, it maps the topography. It's like a dagger, you know, Medosha or I don't know, Makofera, right? Imagine Makofera, something like this. If you drag it on a surface, what happens? Yeah, when it comes to something higher, it goes up and then down and so forth. That way, it maps the topography. It works by measuring a laser scattered on top here. I haven't shown it here, but there is a laser on top of this tip, which is very sensitive to the motion of the tip. And that's what gives you the topography. But on the other hand, the light that you shine on the tip is independent of the topography. It is another light you focus here, which gives you this nanoscale information. The two are completely different and goes to different detectors, so completely separated. So, and I see thumbs up. So, okay, great. So we also do simulation, like Dr. Saifu said. All experiments are better. This is my statement, supported by theory. It's just fun, right? It gives you more information. It allows you to understand physics deeper. So theory and simulation are always part of our experiment. And we, in fact, simulate completely our experiment. We have a tip and a sample. We get this excitation, and this way scattered light and all of that by simulation. So we can compare our experiment with simulation. So what I'm going to do is I'm going to give you 3 examples. Okay, I hope I'm doing well on my time, and I'm going to give you 3 nice examples at very different energy scales or ranges. Okay, I will give you example first in the mid-infrared range. That is around 10 micron-ish area, where we can study quantum properties of materials using this technique. And then I will tell you about very low energy photons, the terahertz photons. These are extremely long, very long wavelengths, range like 300 micrometer long wavelengths range, where light has a very small energy and very interesting to investigate matter in that scale. And then in the visible range, this is the range that we see. But before that, I'm gonna let you visit my lab. Some of you are hopefully not sleeping there. And I want you to wear your mask, and I'm gonna take you to through a tour of my lab, okay? I just Googled this guy from a nice mask here, and I also heard some rumors that you guys have some amazing discovery of masks that are super protective. I'm not sure how true it is, but anyway. Okay, let me take you through my lab. We have 2 labs, and this is a simulation done by one of my undergraduate students. And as you walk into my lab, it's as clean as you see it, okay? And we have 3 tables. In the first table, we have what's called the infrared range. So we use infrared photons in the first table here. And then I kind of lost my mouse. I don't know what happened? Okay, I found my mouse. Just go back again. So yeah, so in the first table, we do infrared mapping. This is where we do infrared spectroscopy at the nanoscale. In the second table here, we do terahertz mapping. And then we have another room where we have this visible mapping. So the three spectral ranges that I gave you, that I'm going to tell you, are done in these three different laboratories. So as we go along, I'll tell you more about how we use this technique to investigate. This is the schematics of this, is actually a nice schematics that shows you the experimental setup. You come in one arm of the, from one side of the tip, and then scatter light through the other, and to do imaging at the nanoscale using this technique I told you about. Okay, so let's move into the first example. So, so what I'm going to tell you is how we can image, look at what are called polaritons. Okay, what polaritons are and how we can image them using this scanning near field optical microscope. Now, what are polaritons? So you may have heard of this this term before. It's a very intriguing kinds of particles. Normally we know light, right? Like photons, and we know matter, like particles, electrons, protons, and so forth. These are a combination of these two. It's a hybrid of light and matter. So it behaves like light, but it's not just light. It behaves like matter, it's not like matter as well. So it's a combined system that moves and does all kinds of things. So I'm going to show you how you can image this. There's a huge interest currently because these kinds of quasi-particles are very interesting for nanophotonics applications, for nano-optics applications, for quantum information, and so forth. So the most studied, these quasi-particles are called the plasmon polaritons and phonon polaritons, and some exciton polaritons studied. But these Cooper pair polaritons and Magnon polaritons have not yet been discovered. So, for some of you out there, here is an opportunity to be famous, right? So these are not experimentally detected yet. So specifically what I'm going to tell you is how we can not just map these moving quasi-particles, but in fact control them at the nanoscale at will, as we like, turn them on and off by using phase change materials that change their phase from metal to insulator at the nanoscale. And I'm going to convince you that we can use vanadium dioxide to do that. And just very brief introduction to vanadium dioxide. It's a material, very interesting material. At room temperature, it's like, it's an insulator, like a rubber. It doesn't conduct electricity, nothing, just uninteresting, an insulator. But then you heat it up a little bit to like, 60 degrees centigrade, a little bit above room temperature, and it becomes a metal. Weird, right? Not many things do that. If you heat a rubber, it just melts, doesn't become a metal. And then when you cool the temperature down, it becomes a rubber again. And you can do this forever. So it changes phase from one to another, as by the temperature. So this is very interesting because you can, there aren't that many materials like that. There are some materials, not all materials do behave in that way. And the change in the phase is dramatic. The resistance, resistance determines, it's another language to talk about insulator, metal, and semiconductor, right? So the resistance of an insulator is very large compared to a metal, right? And that resistance change is like 5 orders of magnitude. It means 10 to the 5 change when it becomes a metal. So there's a huge resistivity change, and it follows sort of this kind of curve. If you draw the resistance as a function of temperature curve. Now, this region is very interesting. The region where both of these phases live. It's called the phase coexistence region. That means both the metallic and the insulating phase of this material live together. And that allows a very nice kind of control. So here is, for example, an experiment we did where we use, we put these gold structures. These are called polaritonic or plasmonic materials, and we can control their dipolar modes by changing the phase or by heating this material. So when you heat it, the bright things you see here are the metallic phases of vanadium dioxide, and the dark ones are the insulating. So you can see that by heating it, you can change part of it as a metal, part of it as an insulator. And depending on where this metal is sitting, you can turn on and off its plasmon properties. So the same is true here, which is a different crystal. So what I want to tell you in a little bit more detail is how these propagating polaritons can be controlled by using this phase change material. So for that, what we did is we collaborated with a group at Vanderbilt who are experts in making vanadium dioxide crystals. These are single crystalline materials. And then we exfoliate this hexagonal boron nitride. Hexagonal boron nitride has a phonon polariton modes that can be excited on its surface. And then we come with a tip and excite this propagating wave. So you can see these waves propagating this way and also reflected from this edge and propagating upwards. So these are plasmon polaritons. This is what the experimental setup looks like. So you have a tip, you shine light on the tip, as I told you earlier. Then that light is confined below diffraction, and the momentum mismatch between the light and these propagating polaritons is now blocked or is removed by the tip. The tip kind of breaks this momentum mismatch. So it breaks the diffraction limit and momentum mismatch, and therefore allows you to couple to these propagating modes and image them as they propagate. Then we heat the sample. Then when we do that, what happens is part of the sample becomes metallic. So whenever you see bright things, it means high dielectric constant on the sample, means the crystal has changed into a metallic phase. And as you heat it further, the metallic phase starts to appear everywhere in the sample, and then you can reflect these polaritons at the interface of the metallic and the insulating phase. So imagine these quasi-particles, these light matter hybrid particles, which we call polaritons, propagating on the surface. And then they come in to this dielectric metallic interface. Then what do? They reflect. In fact, what we found out is they behave just exactly like light. You remember your Snell's law? Who remembers Snell's law? Yeah? When light goes from one medium to another medium, it diffracts, right? And it refracts towards the normal or away from the normal, depending on the dielectric, the optical constants of these two media. And it turns out polaritons do the same thing. As they propagate, they find a medium with high optical constant and then a low optical constant, and it turns out they also refract, just like light. And we actually found that for the first time. This is the first work which showed that light polaritons refract just like light following Snell's law. We also found out that they're extremely sensitive to the optical constant of the surface. As they propagate, they sense the change in optical constant and change the wavelengths and so forth, just like light, right? When light goes from air to water, what happens? It slows down, right? It slows down, the frequency doesn't change, but the wavelengths change. And that kind of change is exactly what you observe also in these polaritons. Here is a very nice example. So we created a polaritonic material on top of two materials. So here is vanadium dioxide, and there is a gap in between. This is a nanoscale gap, and then you have quartz. Then we exfoliated HBN, this phonon polaritonic material, on top, and then shine light and excite these polaritons, these waves, these quasi particles. And as they propagate, you can see, even though this is the same material, the wavelengths, which is determined by measuring the spacing between two of these fringes, is different at different places. Here it's wider, right? The spacing is wider here compared to here. And it's different here. And it's the widest here. The reason for that is, as these things propagate, they sense the underlying material. And whenever they come to a very low optical constant like air, then their gap becomes larger. And as they pass through very high dielectric material like metal, for example, semiconductor, their gap becomes smaller, their wavelengths become smaller, just like light, right? When light goes from an optically dense to optically less dense material, it refracts away from the normal and so on. So we observe similar behavior as well. So we found out this, I'm going to skip this, for the first time, and we did also simulation to show that these things refract following Snell's law. It was very exciting to see this actually for the first time, and if you draw the sign of the angle of refraction with respect to the angle of incidence, just like light, you find a straight line, so as you expect in Snell's law. So this was quite a hit, and we're very excited about this work. And what other thing you can do is you can also filter out the different modes. So for example, if you propagate these things, then as they pass through from one medium to another, they refract, as you can see here, they propagate this way, and then they change their paths now, right? Just like what you expect with light. But in addition, you can also see that the different modes, there are these bright things, and then there are the smaller details in there. So you can separate out different modes by letting these things propagate across different optical media material. So, right, so I want to go a little bit faster, so at least I can cover one more thing for you. But from this example, I showed you that we can create reconfigurable by changing the phase of things, create a refractive reconfigurable medium at the nanoscale. And we can also show that, we have shown for the first time that these quasi-particle propagations follow that of the behavior of light, like in Snell's law. So for more details, we have a number of papers published on this on my website, so you can find out these papers as well. Aidan, did you raise your hand?
No, this is it wasn't for me, but there was a few questions, but I think we'll wait until you're concluded.
Okay.
So please keep going.
Sure. All right. So let me now give you another example in a very different energy scale. These are, I want to just tell you a little bit about terahertz nanoscale imaging. Now, terahertz is an interesting spectral range. It's not very well, it's not as studied or as used as that of infrared or visible. So it is an energy or a spectral range between 1 to 10 terahertz, which is around 3 millimeter to 30 micrometer range. For example, here from 100 gigahertz to 10 terahertz. This is what's roughly defined as terahertz. And so imagine a laser or light with a wavelength of millimeters. That's quite long, right? For example, in the visible, the wavelengths we use is, 600 nanometer, 500 nanometer. Here you're talking about millimeter long wavelengths. So as a result, the energy of these photons is very small, and they're comparable to that of thermal energy. Like where you're sitting right now, you feel heat, right? There's thermal excitation just because of the photons that live in that kind of temperature, and the energies are comparable to those energies. So you can study some interesting phenomena such as molecular rotations, lattice vibrations, spin waves, and for us, what we are excited about, what we use terahertz is to map conductivities of material. So let me show you an example. Is another kind of quick. Probably I will just skip for sake of time this, but let me show you the schematics. Here is the tip, and again, you shine light on the tip. In this case, the light you shine is a terahertz light. Remember, your resolution is not determined by the wavelengths. That's the power of this tip focusing. Your resolution still remains 10, 20 nanometer, depending on the size of your tip, even though you use a very long wavelengths. And so you can image nanoscale excitations or phenomena by using this technique at terahertz wavelengths. One important thing when you work with terahertz is you have to avoid water, because water absorbs terahertz photons. So if you do your experiments in ambient condition, like right now, for example, if I just bring tip, shine light, and try to image a sample, this is the kind of spectra I would get. Very messy because of water. But if I enclose my setup and then fill my setup with nitrogen, kick water molecules out, then my spectra becomes very clean. The spectrum becomes very clean. So we always have to do that. So that is kind of the cost you have to pay for working at this energy scale. But the results are very interesting. So we can map, we can quantify, in fact, the conductivities of materials. This was the first, by the way, this technique was first demonstrated in my lab. We called it terahertz time domain nano imaging. We kind of combined far field terahertz spectroscopy with the tip, basically. So by combining this far field with the tip, you get the nano there, and you can do imaging at a very small scale. And we showed, just skipping the details, we showed that we can quantify what the carrier density is at each point at the nanoscale. This is a sample we got from Intel. It's called the s-SNOM, static random access memory sample, and they dope, this is a silicon wafer that is doped with different levels of carriers and P carriers, and we can map those and give you a number, and we compare our mapping with that of what the company says. Makes a lot of. Okay, so in the end, what you get is something like this. So you can show the conductivity map of a material at a very small scale. This is about 1 micron by 0.5 micron scan, and what you see is every pixel here tells you the conductivity or the carrier density of the sample. So this becomes extremely powerful in that way. So at terahertz, you can the photons are very sensitive to carrier density changes, and that we can take advantage of using this kind of technique. So kind of rushed through this, but as I briefly mentioned, we first demonstrated this terahertz time domain nanospectroscopy technique, and we were able to map the carrier density of materials at nanoscale by using these kinds of techniques. How am I doing this time? I have about 10 minutes or so, is that right?
Correct.
Okay, great. So let me tell you very quickly again on the visible side of things. So in the visible spectral range, what can you do using a technique like this? If you can break the diffraction limit and the momentum mismatch between light and polariton's, what kinds of things can you learn? Now, you can take this technique to the next level. So far what I've shown you is elastic scattering. You come with light and you scatter light at the same wavelengths. So this is an elastic scattering, and that tells you about the optical constants of the sample. But you can also learn about inelastic scattering. You can excite the sample and measure photoluminescence or Raman signal at the nanoscale. So the tip allows you to get PL and Raman. PL stands for photoluminescence, and Raman or vibrational modes of a system or a material at the nanoscale. So this is extremely powerful. So I'm going to show you the setup one more time. And this time I know that some of you are checking your email and getting bored. So I'll put some music for you. So this is my lab again. I'm going to show you a little bit more detail about the visible setup. So here is my, okay, so so here is the setup again. So you can see that there is a tip there. So let me see if I can zoom in. So see, as you zoom into the tip, so here is your tip that I've been telling you. You come in with light from one side, excite the sample, and you get photoluminescence or Raman signal, and then you scatter that on the other side, not back scattering, but forward scattering. So you could do elastic scattering on one side and elastic scattering on the other side. So by doing this, you can map the photoluminescence and the Raman modes of a sample. And this becomes also extremely useful. So we can also do this at low temperature. We can go down to 4 Kelvin. So this is it's close to the absolute cold temperature in the universe, right? Very close, 4 Kelvin, right? We can go down to really, really cold temperature and be able to map photoluminescence and Raman of a system. And there you learn new things. You get clean spectra without thermal fluctuation, and some new things appear at low temperature. For example, superconductivity and other things. So we could do things like that. Although in this case, when we go to low temperature, we are sort of limited by diffraction. We cannot do that with the tip at the moment. Okay, so what can we do? Okay, this is what the setup looks like. Here is your tip. You shine light, focus light again, but instead of back scattering elastic signal, you forward scatter inelastic signal, Raman and photoluminescence. So I'm going to show you some results. We studied what's called a hybrid or a heterostructure of single atom thick material. So much of the material has only one atom thick, right? You probably heard of graphene, right? Graphene is, you get graphene from graphite, a single atom thick, and it's one of the classic quantum material. All its properties are very exciting, right? Many of its properties. But the same is true with what are called transition metal dichalcogenides that are also single atom thick. But these are unique because this particular sample is unique because you have not only just one, but two of them together. They're kind of connected. Remember those blankets, or sheets that have different colors attached to each other, right? It's like that, except that these are single atom thick and there are two different things attached. And so the outside is called tungsten disulfide, the inside is molybdenum disulfide. And then there is a very interesting interface region. If you look at atomic scale, this is how it looks like. These are actually atoms. This is done using electron microscope. And you can see, you can identify which one is tungsten, which one is molybdenum, and how pure the sample is, and so forth. And these are the photoluminescence and the Raman signature, or signatures of the two materials. One is tungsten disulfide on the outside and molybdenum disulfide on the inside. Now, the power of the technique I showed you is you can map any region of these kinds of samples at 10-20 nanometer spatial resolution and be able to get photoluminescence image of the sample. That means you're excited and the sample emits, and that emission is collected locally at the nanometer length scale. And this emission could be photoluminescence or Raman, right? The two give you different information. In the case of photoluminescence, you learn about the band gap, the electronic structure of the sample. And in the case of Raman, you learn about the structure of the sample, right? Vibrational modes of the sample. So what we do is we come in and sit at one point, take a spectrum, move to the next point, take another spectrum, and so forth, and then form a three-dimensional cube. So the XY axis here is the sample axis, and the Z axis is the energy axis. So this cube is the photoluminescence information. It has a lot of information about the sample on its electronic properties. So then what you can do is you can look at how these things evolve over time, how these things change over time, as for example, the material degrades or something like that. And then when you want, you can just slice this cube at any energy you want, and then you can map the emission at a particular wavelength. For example, we know that tungsten disulfide emits at 1.94 electron volts. That's where the peak of the emission is. And you can see that emission mapped out on a two-dimensional surface. And then if you now slice this cube at 1.81 eV, then you can see the emission from the inner structure, which is molybdenum disulfide. And what we found out is, as you bombard these single atom thick materials with light, they degrade, they fall apart. And as they fall apart, their photoluminescence also changes. As you can see, the outside one quenches. These are different days. So you do the experiment at day one, you get this very nice emission. This bright brown color is emission. And then after 5 days, it's already degraded. And so some parts emit, other parts don't emit, and so on. And then eventually it completely dies. So you can follow this evolution of the sample at a small scale by imaging it in this way. And there is also the interface I talked about between, so here I showed you, this is an optical image of the sample. You have tungsten disulfide and molybdenum disulfide, and then an interface. That interface is very interesting. What happens there? As these two materials connect, what kind of connection is that? What kinds of electronic structures are there at the junction? These are the sort of questions we can address where far-field techniques cannot, just simply because you can't see at that scale. But here we can try push the limit of this imaging and be able to resolve what happens at the interface. And although our resolution is not quite atomic scale, as I said, we're limited by the size of the tip. And in this kind of experiment, we're also limited by emission coming from far field. But nevertheless, we can see the interface by mapping in this way. So you can see that tiny interface between the two materials by doing some signal subtraction. So you can do the same thing with also, to compare how different materials degrade. I'm going to skip this. And now the beauty of the technique I showed you is it combines photoluminescence with elastic scattering, right? So you can just switch your mode. Basically, you can forward scatter the inelastic light or backward scatter elastic light. So these two give you different information. In the case of the forward scattering, you get PL and Raman. In the case of backward scattering, you get elastic information about how the system dielectric function change as it degrades. So what you see here is the sample at day 1, and this is the sample after 100 days, 103 days, right? So you can see the optical image is very, very different between these two. This corresponds to this, and this image corresponds to that. So what happens? Why is this only bright in the middle and not on the outside? Well, it degraded, and as it degrades, its dielectric function changes. And that's what you see here reflected on these contrast images. Okay, and you can also do the same with Raman. So I'm going to skip this quickly. And we also did high resolution electron microscope mapping of the sample to show that the alloyed samples, when you mix these two different materials, for example, at the interface, you have not only molybdenum disulfide, but you also have tungsten disulfide mixed in some proportion. That kind of mixture allows the system to be more robust, or the material not to degrade. And for that, we did electron microscope imaging at different dosage of electron energy, and showed that alloying in general gives you more stable materials. And you can also learn about what the excitons are doing. Excitons move around as the material degrades, as it stretches and strain affects their dynamics and localization. And you can also map all of that by doing these kinds of imaging. This paper just kind of sort of came out. Again, we demonstrated the first time combining near field elastic scattering with inelastic scattering by using these kinds of factors. So I think I'm pretty sure like I am over time now, so I'm going to skip all of this and tell you that the conclusion for this part of my talk, I showed you very briefly how you can combine scattering type, elastic scattering, at nanoscale with elastic scattering, such as Raman and PL at the nanoscale in one setup. And this becomes a very powerful tool to investigate what happens to materials at that scale, and combine sort of the elastic information with elastic scattering information on the sample. And with that, I'm going to thank all my group members who have done, just about everything I showed you. I just talk about their results. Students actually are the ones who do the work, and I have a lot of collaborators as well at Vanderbilt and Kansas State, and also at in Germany with Nespe company, and also Ryan Hill and Brown's group. So, and the talk, all of the results that you saw, the work was supported by the National Science Foundation and by the Air Force. So with that, I'm open for questions. If you ask me, I'll tell you why I am showing this rat. Okay, there is a deep story about that, but if you ask me, I'll tell you more about that. Kasa, I think I leave it to you. Who's moderating this? I'm done, and we can go into questions.
Okay, Eden or Casa.
Okay, I can moderate. Thank you so much. This was a brilliant talk. I myself have many questions, but I will always give time first to the students. One question was, can you briefly talk about phonon polaritrons and what their applications are? And then we had some discussion about how we can collaborate with EPS in Ethiopia and researchers in the US. So we'll answer that later.
Excellent, very nice questions. Whoever asked what's the application of polaritrons, really that question is very, very nice question, because it is sort of an upcoming field, and they are very interesting from a fundamental physics point of view. There are potential applications for nanophotonics. One important thing to realize is these kinds of polaritrons are sub-wavelengths. That means, as I have shown you here, when they propagate their wavelengths, here is a nice schematic. So the wavelengths or the spacing between these two fringes, these are waves that propagate, determines the wavelength. So this is lambda over 2. So their wavelength is about 400 nanometer. But remember, I am exciting these polaritrons at mid-infrared range, somewhere around 7 micrometer. So imagine you have a 7 micrometer light, and then you get a nanometer propagating wave. So they are diffraction. I mean, they break the diffraction for you. They confine light at the nanoscale for you. So that's a huge advantage, right? So it's limited by what you can think of to use them. But the important thing is they live below the diffraction limit, and they propagate. So you can use them, for example, for potentially transmitting information from one point to another. Right? I can give you an ideal example. For instance, say you have a quantum emitter of some kind, and it's somewhere here, for example, where my cursor is, and then it's coupled with these polaritrons, and then imagine that coupling propagating to another point. Right? This would be, for example, a huge kind of application. But I cannot tell you, from a scientific point of view, we use them to investigate materials at the nanoscale. By just launching them and looking at their behavior, you can learn about the material underneath. For example, just by looking at these waves, I can tell you that the wavelengths, the dielectric constant here is smaller compared to the dielectric constant here of the material that's underneath this emitter or this phonopolariton. So you can use them as a probe as well. So, but it is sort of still, I would say, on the works. For example, I can tell you like polaritonic laser or something like that. Particularly these kinds of propagating modes. Now, the other important question you asked about how we can collaborate, I think this is quite interesting. The first thing to do is, of course, as I told you, especially for students, to connect with us, right? That would be the first important step. To just sit down, find a website, send an email. That's a very good start. And if you wanted to, for example, apply for grad school, or if you have some kind of calculation you are doing that's applicable to what we do, then I think that would be a very good conversation starter. So send an email and ask. And there's a lot more help than you can imagine. I mean, I sometimes wonder why students don't connect with me. When I was a student at AU, I remember trying to find people. Those days, internet was so rare, and trying to find people. Who should I connect with, and so forth. Today, it's so easy. You just go to a coffee shop, or for free, go to Sheraton or something, and just shoot an email, right? Just like that. And you should really take advantage of people like me. There are many of us, people who give a talk in this platform, and others be very responsive to your questions. So I would say connection, starting conversation is really a good beginning.
Thank you, Dr. Johannes. Another question. Are these types of methods that you're using for characterization primarily also able to propagate or give you information deep inside of, for example, a vertical heterostructure instead of a
lateral? Yeah, that's interesting. So I guess the question, to rebrief the question, is how deep can you probe things? Is it just a surface probing technique, or can you go deeper? The answer is it's limited by the skin depth of the material. So ultimately, you focus light on a tip, right? And that focusing has to do with, so for example, if I show you these schematics, you focus light on this tip. So you have this very confined light, and you bring it close to a sample. So how deep can this light penetrate and probe? Depends, of course, on the material, which is a formal way of saying that is the skin depth of the material. For example, metals don't allow field to penetrate them, right? As you know. Whereas insulators have allow that kind of penetration. So that's one thing. The other thing is also, it depends on the apex radius of the tip, right? The confinement depends on the structure of the TPUs and the size. So I would say it is a surface sensitive technique to be safe. You can probe maybe deep down to, say, depending on the material, 10 to 100 nanometer down, maybe. And you can play some tricks with tapping amplitude and so forth to learn about subsurface structures, but not more. Like you cannot, for example, probe something a micron down or something like that. So it's mostly surface sensitive and very good at that. I think that's probably the best way to put it.
Just go ahead.
I can't hear anyone yet.
Gamaches, I think you are still on mute.
No, can you hear me?
Yeah, can you speak a little bit louder so everyone
Okay, I'll try to do that. So thank you very much for the great talk. Really, I was so impressed. But I don't know how much you catch me up because the concept is advanced. I don't know. Actually, I'm a PhD student, and actually I'm a lecturer from Mati University, but I am a PhD student at this.
Okay.
But the concept is really very interesting, and but it is advanced, as you can.
Yeah, I can imagine that.
I don't know how much you catch up with this undergrad. Anyway, it's very interesting and impressive. Really, I would like to say thank you for all points you already raised. So maybe I don't know. Maybe I didn't understand, or maybe I need more elaboration on some concepts through this talk. So, would you please comment on this magnon polaritons? Maybe please, would you bring us back to this polariton around that slide?
Yeah. Yeah, unfortunately, it's so I apologize. The talk is a little too advanced for undergraduate students, but it's.
I feel as if I am following American Physical Society.
Yes, I absolutely. Next time I'll try to make it a little bit more understandable. This is a kind of talk that was sort of, to try to kind of give you a flavor of what we do, as opposed to introduce something deeper. That wasn't the goal. My goal was to just give you an overview of the sort of things we do in quantum materials. So, but you asked about Magnon polaritons. The answer is I don't know very much about them.
I mean, actually, I know
do not know about
from theoretical perspective. I have some. I may a little bit. I may understand some the rational behind, but what is the physical meaning? I mean, really, how can you manage this one when you do your experiments, especially this?
Yeah. So right. So okay. Experimentally, the technique I showed you turned out to be extremely valuable to image these propagating mobs for two reasons. One is, of course, you break the diffraction limit. But the most important reason for these kinds of propagating mode mapping is the momentum mismatch. So, for example, I showed you, these phonon polaritons here from boron nitride. This is hexagonal boron nitride phonon polaritons that propagate on the surface. Now, if you want to do this in the far field, that means if you don't have the tip and you simply shine light, then you cannot see these kinds of waves, simply because you can't couple to them because the light momentum is different from these propagating particles, quasi-particle momentum. So because of that mismatch, even though your energy is correct, these are excited at 6 micron, 6.8 or so micron, you have a laser at 60.8 micron, but still you can't excite them in the far field, just because the momentum is different. But the tip allows you to break that momentum mismatch. How does it do that? Well, when light comes, light diffracts. It diffracts around the tip, confines around the tip and diffracts. That means all kinds of momenta of light are produced around the tip. Some of that would couple with the material. In the free space, light will have a certain momentum, fixed momentum, and that simply is too small compared to the quasi-particle momentum. So there is mismatch there. It's like trying to chase, if you try to chase, even if you have, simply if you try to understand kinetic energy versus speed or momentum, right? For the same energy, you will have different momentum, for instance, and the mass can make up for. So if you think of E equals P squared over 2m, and you have two particles that have the same momentum, P, but they can have, the same energy, E, P squared over 2m is the same, but they can have different momenta, right? Because the mass can make up for the momentum difference. So that momentum mismatch prohibits you from exciting these things in the part. So these kinds of techniques are the best for that. You can map this propagating mode. So if these Magnon polaritons are real, theoretically they are, like you said, experimentally they have not been observed yet. Then most likely this would be done at low temperature, I would assume, and they can be imaged. And a number of groups actually are actively trying to do that at the moment. I am not doing this because the kinds of tools I showed you only work at room temperature and at high temperature. I do not have the ability to image at low temperature. So that's a limitation.
Thank you very much, Dr. Johannes. Unfortunately, we are out of time. We have to start with the next speaker, who's Dr. Tasamma Gabriel, who is at the who works at the National Science Foundation. Okay, is Dr. Tasamma, are you here?